Hi, so what I want to talk to you guys about in this video tutorial is dealing with point data for different animals. So this is especially relevant for the two final project suggestions, one dealing with bears in Newfoundland, where we have collar data for, I forget, 8 or a dozen bears or something like that, and the other dealing with the pumas, the mountain lions in Southern California, also collar data, I think in this case for something like 20 cats in Southern California. So let's go take a look at those data sets. So here is what the data set looks like for the different bear individuals. So these bears are in Newfoundland, right? So up in Canada. The spatial data, so this project does come with some spatial data. So it has some elevation, it has some other shape files like the extents of Newfoundland, for example, and some roads and rivers in Newfoundland. My experience with this particular data set is that those spatial data layers aren't particularly useful for the analysis because they're just really far away from where the bears were. The bears were kind of like out in the boonies, away from the roads, and they're entirely in forested areas. So an actual kind of spatial comparison between bears and spatial data isn't as interesting as just what the bears are doing generally. So this is true for the mountain lions data as well. There are in this data set both male and female individuals. So in the bears, that's in each table. For the mountain lions, the data layers are actually labeled, where's the pumas? They're labeled F or M for male and female cats. All right, so back to, I'm just going to use the bears one as our example here. Okay, so here are our bear data for Newfoundland, and we can bring one of these guys in and open it up and make sure that it looks like something, right? Most important thing to identify in here is your X and your Y right here. So there's our X and our Y. And then the first thing that we want to ask ourselves is, are these data a geographic coordinate system? And when I look at these, I can tell these are not in a geographic coordinate system because these data are way too big. These numbers are way too big to be latitude because they're bigger than -90 to 90 in the X direction and much bigger than -180 to 180 in the Y direction. And so ideally, we would then go look at some metadata, find this like README file, whatever it is, that tells us what that projection should be. In this case, actually, that information is not provided, which is a little obnoxious. But what is provided are a bunch of other shape files of Newfoundland and other stuff going on. And these data sets do have a projected coordinate system that it turns out is the same as what the bear data are in. So we can make an educated guess here that that's what this is going to be. And the nice thing about GIS right now is that it will always suggest to you whatever the coordinate system is of the data frame. And since we just brought this first shapefile in, it assumed that coordinate system. And so that makes our lives a little bit easier right now. We just have to say X is X and Y is Y, and we know that those are in a UTM coordinate system, zone 21 north, and the datum is NAD 1983. And so this should hopefully show up some points in Newfoundland. That's always a good first step. Remember from Lab 5 that this is just the event layer is basically just a visualization. It's not actually data, spatial data. So if we want the spatial data, we need to export it as spatial data, this there, and let's save it as the coordinate system of the data frame so that we've got a nice projection, well, as the original layer, but we want to make sure that there's a projection on here, right? So you can just double check, go back into properties. Yep, all right, still have points. Shouldn't need that stuff anymore. I can just focus on the points. So with the bears or with the pumas, one of the first things that you need to do is to get point data to become a line, basically. So that is the cleverly named tool, points to line, down here. Hello tool. And we want to input our shapefile. Now, one of the things that's a little annoying about points to line, and I've tried it, like there should be a way to tell it to split the line based on this field, but it hasn't been working too well for me. So generally what it's going to do is just create a single line connecting all of these points. And what I mean by single line is that when you open up the attribute table, it'll just be a single feature. Okay, so here's our line. Nice brown, good choice, GIS. And when we open this, it's just a single thing for that entirety of the line, which is a little annoying. It would be nice. Oops, stay over there. I just want this to come out. Okay. It would be nice if it just automatically, you know, like created all of the different things, but it would be nice if it automatically created 4950, which is I think the total number of points in here. It should be able to create 49 line segments, but that's not the way it likes to work. So we have to trick it a little bit, which is actually already up here, but this almost a split line at points, but what we actually want is to split the line at vertices. The vertices are basically, if I zoom in, you remember that, you know, like any of these places where it turns, it's going to connect straight line segments between all of those original points at the edges. So all of those original points where it's turning, they're embedded in this line shapefile. They're just vertices. So we can split this whole thing based on those vertices. And I'll call it line. Maybe I should add an S there. Split. Let's see what this does. Okay, so now it looks about the same, but in this case we have that 4949 individual line segments from that starter file. So we can do now is measure the distance of all of those segments, right? So we can add a field, we can call it distance in meters. I want to make sure this is floating point so we get lots of precision, and calculate my length in meters. Good job, GIS, anticipating my every need. Okay, so now I can see that some of these line segments were pretty small. I can sort it, right? Some in 2-hour periods, this bear barely moved at all, just hung out, sitting there. Sometimes it moved, well, that feels a little unbelievable, but 40 kilometers in a couple hours, maybe that was longer than a couple hours. So, you know, several kilometers of the bear is, you know, on the hoof, basically in these time periods, not on the hoof, on the claw, whatever the right analogy is. All right, so we have 2 pieces of information. We have information about, for example, the time, the date, so we could get the season, for example, or the month out of this information. This day, this is a Julian day, so 151 means 151 days from January 1st. So we could try to lump those. We also have information about how much it's moving during the day versus at night, right? So lots of different ways we could analyze this information and would like to analyze this information if we also had length appended to this, right? Okay, well, here's the great part, right? You guys have already done a spatial join, Lab 7, so we can pull that attribute information into, we want our line split, and the only information that we actually need is this distance, right? We don't care about the ID, get rid of that. We just want distance in meters, right? So off we go. And once we do this, we should be able to open this attribute table, see all of the same original information, plus, didn't work too well, did it? Pause. All right, so I just futzed around and figured out what was wrong, and it turned out I had a couple of things selected. So GIS was doing exactly what it should do, which is to only operate on the selected features. So I'm going to do this one more time and call it intelligible. Don't need this. This is the one again that's coming from, I don't need the ID of each of those things from that other line file. I just need the distance. And this time, hopefully, it will have given me that distance moved for each of these things, everywhere from not very much all the way up to quite a bit, right, during that time period. So this is a really useful piece of information, right, for this animal, which is I can get basic statistics for, on average in a 2-hour period or whatever it is. And here the animal moved 0.5 kilometer. I could also do a summarize based on how much this animal moves in the night versus in the day. And how do we do that? Remember, summarize at minimum would just give you a count of the number of nights and the number of days, the things that are similar in this column. In this case, though, there's an added trick, which is that we can sum together all of the distances for the nights versus the days. And then in our output table, you can see that for the 2979 days, I guess I want an average rather than a sum, huh? That would make more sense. Let's do that again. Average distance moved during the nights versus the days. On average during the day, it's moving 0.6 kilometers. On average during the night, it's moving 0.5 kilometers. Another thing that I might want to do, though, is summarize it in a different way, like based on the dates, for example. This might take a minute, but where did my Julian days go? Here, they went in here. So if just going to hide these guys for a minute. If I look at my, I think that only hid the first one. Forget that. I could also manually do a month thing here and say, let's see, Julian day. So you can find Julian day calendars. So for example, January goes from 1 to 31, February goes from 32 to 60. That first date was 151, so June, let's call everything in June 153 to 182 in Julian days on here. So here's where did our day go? So I can sort based on the day, and let's just, for argument's sake, let's see. So it was 88 in our Julian day calendar. That is end of March. So let's call it like April is 92 to 121. So I can select all of the ones that are between that and 121 as April. And remember that we've got this field calculator over here, which will only operate on the ones that you've selected. So if April is month 4, then I can go ahead and put a 4 in all of these selected ones. And then let's see, what is month 5? May is 122 to 152. So some of this is like, depending on what the analysis is that you want to do, you know, you can analyze these things in different ways. So here's month 5 for May, and so on. So like, for example, now I can summarize by month. So I only added April, May, and then like everything else kind of thing in here, but you could do all 12 months, right? Do the average of those. And then let's check out this summary table. So now our summary table says that all the other months, the animal moved an average of 0.57, in April 0.34, in May 0.67, right? So if you had added all of the months to this one, then you would have a nice kind of histogram of average movement per month, which is kind of fun. So those are just some examples of things that you can compare distances by, you know, when in the season it's moving, by day versus night, any other attributes that you think might be interesting in here. Another thing that might be interesting actually is how much movement the males have versus the females, because there are both male and female bears in this data set. There are also juvenile bears versus adult bears. So you might want to say, well, let's do this for all the juveniles, sort of repeat all of these steps, and create some histograms of how far does a bear move, you know, how far does a male bear move through the seasons versus how far do female bears move through the seasons. And just as sort of examples of that, right, you know that we can always export this table. So this is my table of April, May, and everything else, right? Not a very exciting table, but let's call it April, May, everything else. I'm saving it as a text file because I know that Excel can do a text file. And then I'm going to go find my temp file and open this. Whoops. All right, I guess I'll just open Excel here and open it that way. I'm just doing open. And let's browse for that temp file. You're gonna have to tell it all files because Excel will refuse to show you that thing. And then we have to go through the little thing, which is like, well, how do you want to open this text file and how are these things delimited? This part's important. You can see there's commas between all of these. So you want to select commas to get those into their respective fields. And now, you know, you've got month 0, 4, and 5 in these distances, right? So I don't really care about the count. I can move that over here. But if I insert a graph, you know, then I can get this sort of, oops, actually, I guess what I want this to be is just an insert of a graph here. And that'll be ordered. And then I need to tell it, you guys have to play around with Excel a little bit, tell it that this should be labeled as 0, 4, and 5, right, in the chart title. And so that way you can compare, you know, like over a season, what do these things look like? And if you had multiple bears, so like this was, you know, bear, what was it, 0802 or MR 0802 or something like that. Let's say you had bear 5 or something, you know. Just typing in some random values here. Then we can add, okay. Then we could just insert data for both of those, right? And you get a side-by-side comparison of, you know, here's bear 1 and here's bear 2 for each of those, however you wanted to do it. Nice visualizations for a final poster. Okay, so that gives us some lots of bear stuff. One other thing, and all of this, of course, is relevant for the pumas as well. One other thing that you might want to consider doing is looking at the overall range, like the home range of this bear. And one way to do that is this thing called a convex hull, or a minimum bounding geometry. I never remember that tool name. This basically says, and you can see over here, expand this a little bit, that if you give it a bunch of points, then basically what a convex hull does is it draws a polygon that surrounds all of your different points. So here I have, my input data. This is my output in the default geodatabase. And then in this case, I can choose convex hull because I don't want it to be like a rectangle around the thing. I actually want to encompass all of those. And so that should spit out, zoom to that layer, a geometry that encompasses all of these different points, right? And since I saved this into my geodatabase, it should have the total area of that home range in square meters in this case, because that's our projection. And so if you wanted to compare this home range for a bunch of different bears, off you go. Okay, now I want to talk about some things that are specific to the puma data. All of these comparisons of different animals could work in either different data set. For the puma data, because we're in the US, we have the luxury of having additional information that we can compare the puma range to. So I'm going to create a new document, go over to my puma data, bring in one of those guys. Puma data are a little bit larger than the bears. They do have the nice thing now, latitude, longitude, right? I found my X and my Y. In this case, is it a geographic coordinate system? Yes. So that makes my life easier. I just have to pick a reasonable datum and off I go. So X field is longitude, Y field is latitude. Somehow moving my hand always helps me figure those ones out. Because this is North America, let's go with, and I think this is actually in the metadata someplace. Let's go with a standard North American datum, but otherwise it's a geographic coordinate system, easy. Here we are in the world. If we're not sure where we are in the world, we can always grab a spatial data set, like countries of the world from Lab 2, for example, and see if we show up somewhere in the world, looking promising. All right, forget this. I'm zooming to the world and then zooming back in. Okay, and Southern California is indeed where we know these mountain lion data to be, right? So that's encouraging. You can also, I can't remember if we had states. Did we have states in one of the labs? I can't remember. I have states someplace else though. You can always Google states, states and spatial data, or states and shapefile, and you can find that pretty easily. States. Okay, so here's our states, and in fact, I've got counties in here too. Also, you can get counties polygons from the shapefile, or from the census data. What county is this? This is Orange County, California. Okay, so Orange County, California is where this particular mountain lion hung out. It's possible that the other mountain lions hung out someplace else. That lawn, that's nice. Another female mountain lion. Yep. Let's see where this, okay, so this one is way over here, and that is in San Diego County, okay? That is relevant because you want to, if you're interested in mountain lions and when they're crossing roads, then you want to compare it to road file. All right, here's where I get roads from. Go to census tiger line shapefiles from the US Census. And here we are, and down here there's this thing to download it from a web interface. And now I have a choice of what it is that I want to download, and I want my roads in 2019, sure. The tiger data, the lion data are from earlier than 2019, so actually you might want to go back to whatever year they were collected. And I want all roads for California, except I want to specify, let's start with the Orange County one. These are pretty hefty line files. So, you know, I mean, we've got 9 megs, I guess, for just Orange County, but you can download the ones that are relevant to your location or wherever it is that the lion data exist. All right, I'm just going to copy paste those into my temp directory. Went down there. Okay, so they're named this kind of weirdo thing. As long as GIS can read it, I don't really care. Where's my temp directory? Yeah. I'm going to refresh that because I won't see it until I tell it to look for it. And there is our roads for Orange County. Okay, so now we've got a bunch of roads in Orange County. We can do that same thing that we did for the bears, right? We want points to line for this lady, I think, yeah, F121. Points to line for lion F121. Oops, not a shapefile yet. Actually, does that work on here? Let's see. I don't know if points to line works on something that isn't a shapefile. Apparently it does. That's pretty exciting. You don't even need to convert it to a shapefile yet. This had something interesting in it, which is the shape length. But remember, these data are in a geographic coordinate system. So this shape length is 1.9 decimal degrees, which isn't a measure of distance. So don't use that. That's yucky. And in this case, you know, okay, if you wanted to do those host steps that we did with the bears, then one thing that you would need to do is to put the data frame into some sort of projection, whether that's, you know, a state plane system. So you can find the state plane for California, for example. I don't know why there's so many different ones for California. Exciting. I guess they just have a bunch of conic projections that go up and down. So this is lower latitude and we're in Southern California. So let's pick that one. It doesn't actually really matter. It's just so that you can calculate distance. So for example, once I had this one and I had the one that was split up and stuff like that, I could add a field that was called distance in meters. And calculate the geometry and just tell it to use the coordinate system of the projected data frame. And now I've got my actual distance in meters. Ended up being, it's interesting, they both start with 19, that is totally random, 191 kilometers total that this cat moved. Cat on the move, indeed. Okay. You've got roads in a line file, you've got cat movement in a line file. You want to see where those two things overlap. That's actually a clip because you've done that before, or intersect. Let's do it as a clip, right? Because basically we're just looking at the overlap of these two things, the roads and the, what did we call the other one? F121 point to line. Wow, this is a good reason to rename things. So it's F121 road crossings. Clip or intersect should both work the same way. And ultimately, if you're crossing a line with another line, you should just get a point, right? Your output file should just be points of where those two things actually intersect. Let's see if it works. Okay, so it turns out the clip doesn't work. It is an intersect that you need to do. And the reason for that is because the clip tool doesn't allow you to do this one extra thing that intersect does allow you to do. So I am going to intersect my roads with my point to line file. I'm going to call this something intelligent that I didn't do last time. So there's my animal. And here's the key piece. We want the output type to be points because we want the location, the point locations of where that animal has crossed a road. So we'll let that go for a second. Okay, so now we've got the point locations with our intersect of, where this particular cat crossed the road. We actually have the name of the road since intersect does this nice thing of pulling in all of the attributes from the different layers. So that's cool. We know that there are 30 times that this particular cat crossed the road. And you can compare that to the numbers of times other cats crossed roads, or male versus female, or whatever it is that you wanted. And then just as a reminder, because we have all of these point locations of where this animal moved during this time period, if you wanted to say, look at what types of land cover, or look at information about human development, or whatever information you can find off of the California GIS websites or national websites. You learned in Lab 7 about spatial join, bringing information about a polygon attribute into each of those points. And you also learned about extract values to points, which is bringing information about a raster grid into those point files. So if you wanted to do anything like that, there you've got it. And then just like we did with the bears, you can summarize that information, to figure out how much time did this animal spend in various different land cover types or elevation ranges or areas where they're close to people, whatever it is that you're interested in. Okay, well, that took me a long time to figure out how to do all of those bits and pieces, but hopefully that will give you guys a good starting point for analyzing bear data or cat data.